talking about now is important, but it will not be on the exam. Okay, so I've already written the exam, and it's not. But it will be on the next exam. Scalar is a scalar just has a numerical value, but it can be pointed in any direction. There is no direction, right? It's just it's like energy. It's this nebulous thing. It has a quantity, it's a magnitude, but it's not pointing anywhere. Whereas a vector also has magnitude, right? But it's pointed in a specific direction. That's the only difference. Turns out it's a big difference. But then there are, when we do mathematics with vectors and matrices, it's called linear algebra. That's the name. And it follows a lot of the same principles as regular algebra, regular math, but there are some differences. And so I want to highlight here, just for those that aren't as familiar with linear algebra, vector, and matrix analysis, what the similarities are and what the differences are. So some of it will look really basic, but then every once in a while you'll see something that I present that's opposite to what you are normally accustomed to. So it's important that we cover this here, so we're all on the same page. So let's say you have two vectors. Here's a vector A, and we'll get into more details, specific details, examples later, but now it's just sort of getting a feel for vectors, you know, and then how we work with them. And there's another vector. So both of them, you can see the magnitude is represented by the length of the line, and you can see I have direction for both of them. And what we can say is A plus A equals 2A. I know this looks like elementary school stuff, but in vector analysis, like I said, so this is like saying 1 plus 1 is 2, which is correct. But then some things that we see in vector analysis will be opposite to what we would expect. So A plus A is 2A. And we can place the tail of one to the head of the other. So we have, here's A, that's one of those. And now I'm taking the other one and putting it here. And you can see I can replace this with this vector, which is 2A, right? A plus A is 2A. So let's say I place tail to head. So now we can say, let's say you have a vector A and another vector A, but in the opposite direction. So now it's like this. And we're going to add these together, and you have A minus A equals 0. Or A plus minus A. So that one is minus A, that's A, or A in the opposite direction is minus A, it's minus A is A plus minus minus A. Let's say law. So here I have A, a vector A, a that with the given magnitude and direction, pulling on a point. And then I have some other vector here, B. You have a resultant if you go like this, like a parallelogram. The resultant is this. Okay. And this resultant here equals A plus B. So now we don't have two of the same vectors, we have two different vectors. How we actually numerically add them together we'll get to later. But this is just conceptually. We have, you can see there's A, there's B, this is the resultant. So instead of applying a vector, this is a point it's pulling on your structure, let's say, and it's pulling with A at that angle, B here, and instead we can replace those two with this resultant vector, and the effect is the same. Okay? And we have, and then this is parallel to this line is parallel to this, and that point that the resultant extends from the origin of the two other vectors applied to it. So R equals A plus B. So we can draw it like this. Here's A, B, C, this is A plus B. Again, tail to head, right? So we have A, this is the same A and B as up there, but now I'm putting this vector, the tail of this one to the head of that one, and then you can see where it ends up. We just replace this to A plus B, and that equals the resultant, right? So that resultant is that. And it's not just for two vectors, we can do this with multiple vectors. We also have commutative law. That's that A plus B equals B plus A. Again, this may be obvious, but as you'll see, just as you start to get things that everything's obvious, some things aren't like that. Some things are different than regular. So A plus B is B plus A. Again, these are vectors. And so what we mean by that is, this one is A plus B. Now let's draw here. I'm going to draw B first, like this, and then A. And then this is B plus A, which also equals the result. So here we place A and then B, the tail of B to the head of A. Here I'm placing the tail of A to the head of B. So this is A plus B, this is B plus A, but you can see the resultant vector is going to be the same from this point to there, right? Even though there's a different path to get there. Now we got A minus B equals A plus minus B. So here's a point here. Let's say this is A, and let's say this is B. Something like that. So minus B would be like this. So I'm going to draw it again. I have A, and then I'm going to put this B in this direction for A plus minus B, like this. See? This is A and B. So in this case, the resultant is like this, right? That's A minus B. So it's not obvious. And then, of course, you could draw it like this, this. This is the same as you have A, like that. This is A, and then B is So now you can see, looking at this, that the resultant looks something like this. So it's a little strange, right? So you have A, you have B, they're pulling in different directions. So the resultant, you can see, it has this has a direction. This is like, I should make it look like that. This is the same as the resultant up there. This resultant, this is that. So, you know, the line is at some distance between them, and the magnitude is whatever it is, okay? You can see how your faces are a little screwed up for this one. But when you add them, it's pretty obvious. When you subtract them, you have to think about it, right? But we'll see as we go and when we do examples how it works, and then the actual numbers. It's nicer to lecture in person rather than by Zoom, because I can definitely pick up feelings in the room. On Zoom, not only can I not, but not a single person ever asks a question. They're on and they get off, and it says it's as though it's a ghost lecture. Yeah, back there.
So for the subtraction, you're looking at vectors that are pointing in opposite directions.
Well, not opposite. It's opposite to, so we defined A and B. So minus B would be the exact same magnitude, but in the opposite 180-degree direction. So that's what I was trying to indicate. So then I got this B, and then I'm showing, here's A, that's supposed to be the same as that A. And then this B is minus this B, which is like that. So I drew it this way. And the resultant, if you put the tail to the end, the head, you do this, right? That's one vector. The other one has magnitude and direction, so it's the same length, but it's pointed this way, it's like this. And so, and sure enough, the resultant will always go from the beginning point to the end of all the vectors that are going to get. So it's got to be this. And then when you draw both A and B back at the original applet like this, you've got A, which is this, and then this B in this direction, and then the resultant is what I have here. And then when we break them into components, it will become more obvious. We'll have the X components and Y components, and we add those together for the different vectors, and then you'll see how this works numerically. So yeah, it's a funny thing, and this resultant is shorter than A and B too. But it's because they were subtracting from each other. You're not adding. Okay, so this, we have A plus B. Now we're going to make it more complicated. A plus B plus C equals, and again, this is funny, watch. A plus B, bracket, plus C. Correct. And that, and A plus B plus C equals A plus bracket B plus C. And I'm going to write all these ones, and then I'm going to draw all the vectors that are consistent with this, so you'll see what I'm saying. And A plus B plus C equals, C plus bracket A plus B, which equals C plus A bracket plus B, which equals C plus B plus A. So that's what the associative rule means. And then when we sketch it below, it will become more obvious. And again, this may seem like it's trivial, but it actually turns out it's not. So A plus B plus C is the same as bracket A plus B and then added to C. So you can think of A plus B, anything in the brackets, think of those as resultants, not of the whole thing, but resultants of those two vectors. So this is like A and B added together and so on. So let's draw down here. Here's our starting point. I have vector A here, vector B, and vector C, something like that. A plus B plus C is this resultant, right? Like that. But now look, so that's A plus B plus C. And now let's look at this. That's A plus B plus C, but this is A plus B, right? So let's draw the vector for A plus B. That goes from here to here, like this. This is A plus B, right? So you see it's like taking a shortcut. So instead of going A plus B plus C, we go A plus B and then plus C. That's this one, A plus B plus C. Now let's do, okay, so let's do it this way. I'm going to now start with C. So C is like this. Okay. And then I'll put B here. I'm trying to put this same B, same. And then this is A. Like that. So A plus B plus C is the same as C plus B plus A. It's a different path, but the resultant is the same. But look, we have here C plus A plus B. This one here, this is A plus B or B plus A, right? So you can see that's the C plus A plus B. And then we have, you can arrange them however you want. And this is equal to B plus A. Oh. And you can see that this from here to here is C plus B. So C plus B plus A. So that would be another one, C plus B bracket plus A. And in all cases, they equal the resultant. The overall result. Is that clear? So each one of the vectors has a magnitude, which is indicated by the length of the lines, and a direction, which is clear. An angle. We also have A plus A is 2A, right? And B plus B is 2B. So A plus A plus A is 3A. And of course B plus B plus B can be written as 3B. So coplanar forces just means forces in the same plane. There's no component out of the plane. In this case, they're all on the plane of the board where I'm drawing them. There's no component from that. If we're doing three-dimensional analysis, you could do that too with vectors. And then these vectors would have three components instead of two, and part of it would be coming in and out of the page. But everything we're doing right now is looking at coplanar forces. Concurrent forces. concurrent forces or forces that are passing through the same point. Mentioned it a couple of times, was the polygon rule. So here we've got a point on a structure. I have a force applied, let's say. As a force, it's typically considered as a resultant. So you have, as a vector. So you have A, you have B, these are different vectors, and I have some vector off this way, C. And maybe the resultant looks like this. The resultant of all three of those. So redrawing them, putting the tail to the heads, I have, I'll start with A. So here's A. And then B goes off like this. And then C is like this. Right? A, B, and so the resultant, it's not obvious when you look at it like this, but if you put the right magnitude, the right distances or lengths, and the right angles, and you put the tail of one vector to the head of the other, you can see much more clearly that this is the resultant like this, right? Which is what is it. So if I draw it like this, it's not obvious, but if you draw it like this, it's the same, because that's what it is. So if we have A like that, B like this, we can imagine placing B like this. That's a parallelogram. And in that case, that would be our result. So the force F can be resolved into components, and it's typically resolved into two components, as I'll show in the sketches. Here's a force F, and we have A, then you could say here that A plus B is F, right? But you can see here that this is the force, and then if you multiply whatever magnitude by the cosine of the angle, that will give you the A vector, and the sine, force times the sine will give you the B. And then in vector math, A plus B is F. This is when it's right angles, so you can have a little box here indicating that's 90 degrees square. But it's possible, and this is what's interesting about vector analysis, it doesn't have to be broken into Cartesian coordinates or 90 degrees. For example, let's again we have that. Let's say same F as that, and you could split it into this little a, right, and that B. It's still A plus B is F in both cases. You can split it how you want. These are components and these are components. Yeah.
It's kind of like how, well, the problems we did before with beams, you would have a line that goes at an angle and force.
Yeah.
And there's two counterparts. It's like the sine counterpart and that goes.
Yeah, you have the two components.
So that's kind of a similar way.
Yeah. Now remember what I'm talking about. I am talking about forces because we're doing a statics class here. But these are vectors, so a lot of what I'm talking about applies. It could be velocities, it could be anything, right? Anything that's a vector, anything in the physical world that has magnitude and direction. So it doesn't have to be, don't necessarily think of it in terms of forces. Okay? This is general mathematics, how we approach certain kinds of problems. And then we could also have this, here's F, and the two vectors pulling, so this is A and B. And again, you can connect it like that. This is theta. So in terms of the actual application, you can put them tail to head, but in terms of the point on the structure where it's feeling the force, here's the force, and if we break it into components, you need this pulling it over here and pulling up here at that actual location. And it would be true if we broke it into this. So here's F again. And instead we've got this little a like that. And we've got this B like this at an angle. And you got the parallelogram like this. So this A plus B is equal to F just like that A plus B is, okay? But these A and B are not the same vectors as these A's and B's, but they still add up to the F, okay? So you can break it into different components. And then you could see looking at it, here's the point of application of the load, right? And you will think, well, wait a second, this A is same direction as that A, but it's a little less force. You know, so if we replace the force with these two vectors, so instead of the resultant force, we replace it, you say, well, that's, you know, instead of 10 kips horizontally that this feels, now it's like, looks like 5 or 6, right? But because B now is at an angle, there's a horizontal component of that, you add that at this point to this, and that's the full 10 kips still. And then the same argument vertically. Resultant, this is must be the force, right? If you apply these two vectors A and B, and in terms of the actual point of application, we have A, and there's B, and so this is F, right? So again, I've had two two vectors, and if you put them at the actual point of application where it's applied, there's A and there's B, and you can replace those two forces. Let's say there's a cable pulling on the structure here and another one here. We can replace those from an analysis point of view with just this resultant force. And then you put the tail ahead, you can see what the force is, and then you can erase them. These are two separate cables pulling on the structure, but the resultant effect is identical to if we just pulled with one cable in that direction with a different magnitude, right? That's what it's saying. Imagine this is just 2D. We get the same kind of thing in 3 dimensions. The vector analysis allows us to do it in such a way that is clean, and especially when you're imagining go from 2D to 3D, it reduces the complexity. Otherwise, you can't imagine what you're looking at. So here's a good example. I'll give you a numerical hole. There's a bolt that's down into a structure. We have a force applied up of 60 kips. And that's 60,000 pounds. There's another one here at a different angle of 100 kips. 100, so the vector is longer. You see 100 versus 60. And then we can replace those with the resultant. We need to know the angles. This is 30 degrees. And this is 20 degrees. So this all the way around there is 50 degrees, right? 30 and then 20 between them. I have A, B, and parallelogram. This is my resultant, right? So this so this dotted line there is B, that, and then this is the B in my state. This point is this point. So let's first look at A, this is the 100 kips, right? And then B is the 60 kips. That's the 100, this is 30 degrees. So this is 100 times the cosine of 30 degrees, which equals 86.6. And this vector here is 100 multiplied by the sine. And that is 50. We'll draw it again right here. See, for the individual force of the 100 kips, we have that represents the resultant of the two forces that make it up. So we have the horizontal component of 86.6 and the vertical component of 50 pulling. Now let's look at the other force. This angle from the horizontal is 50 degrees. So this is a 60 times the cosine of 50 degrees. 38.6. And this is 60 times the sine, which is 46.0. So redrawing it here, we have these are all in kip units. This is 60, 38.6, and 46.0. So what we're going to do is add the components together. So in the x direction, the horizontal direction, you can see from the 100, I have 86.6. From the 60, I have 38.6. So we're going to add those together horizontally, and then vertically, we have 50 and 46. That would be 96. That's for the final resultant of both forces together. So the resultant equals A plus B. Call this one, this is A, and this one's B. So we have, say, 38.6 plus, say, B. So I have 86.6 plus 38.6. Equals, and then vertically I have 50, 0, plus 46.0. This is 125, in this direction is 125 kips, and 96 in this direction. There's the resultant of both of those forces of A plus B. And the resultant, the magnitude, is 96 squared plus 125 squared square root. It's just the hypotenuse. Those are those two values. This is theta. magnitude here is 158. And then, so this length here is 96, and this is 125. Right? So we have the tangent of theta. This angle is 96 over 125. Which is 0.768. So our resultant is 158. A plus B, add the angle of 37.5 degrees. The arctangent. So we solve it this way, or we'll use trigonometry. So first start with law of cosines. Here's A, B, resultant. We have this angle here, it's theta 30 degrees. This is beta here, this angle. This is alpha there. Let's call it alpha prime. We have r squared equals a squared plus b squared minus 2ab cosine theta. So r squared equals a, 100, squared plus b, magnitude, 60, squared minus 2, 100, and 60, multiplied by the cosine of 160 degrees. And that's, we know that the difference, this was A here, and B, we know that B was up 20 degrees from A. So here's A, and then B, when you put this here, there's a 20-degree rotation. So that's how I know this. I extend this line and rotate it 20 degrees. That's the direction of B versus A. And so I have 180 degrees here, minus 20, that's this beta angle. From here to here, that's where 160 is coming from. So from this, I get this equals 2,476, but that's r squared. So r is the square root of 2476, which equals 158. Same, right? 158 clicks. And then we have to use, so that's the law of cosines, we have to use the law of sines also to get the final angle. And trigonometry. And for this we have sine prime, sine of that little angle there, over B is equal to sine of beta over R. So we can solve for sine of alpha prime. B is 60. So I'm bringing B over here. I know beta. So the sine of 160 degrees divided by the resultant, which we know now is 158. And I get that therefore sine of alpha prime is 0.130. And alpha prime therefore is the arc sine of 0.130, which is 37.5. That's the angle between A and the final result. Okay, and then this angle here is alpha, which is just 30 plus alpha. Oh, sorry. I'm sorry. Alpha prime. I read my notes wrong. This makes more sense. This small angle there. The sine of alpha prime is 0.13. I take the arc sine of that to get the angle, and it's 7.5 degrees. And it was this alpha, this angle, is 30 plus alpha. So 30 plus 75, that's where we get 37. This makes sense. Okay, so we now know that the resultant from this here it says that the resultant is acting at an angle of 37.5 degrees, and the magnitude of it is 100, the resultant, which is 150, and that's kips. So we have a magnitude and a direction. This is the final resultant on the bolt from the two different forces applied. Yeah?
Can you clarify where you're getting 160 from, the 160 degrees?
That's this angle here, right? So what it is we knew that if you go back, here's A vector, the one force, the 100 kips, and here's the 60. There's 20 degrees between them. That was given, right? And so now when I look at this, here's A, and I put B, the tail of B to A. So this has an angle, this has an angle. If I extend this line like this, this, as I rotate here, has to be 20 degrees from here to here. You see that? That's, no? It's the same as this, look. If I take this, it's 20 degrees to rotate to that. I've taken this vector and I put it here, so 20 degrees. So now I extend this line, and I rotate 20 degrees to get to that same vector. And so, if I didn't rotate this, if I was rotating about this point, it would be 180 degrees to get to the other side, right? So now it's 180 to get here, minus that 20, which is 160. That's this angle here. 160. Is that clear?
Yeah.
So the way we write it, then we say, let's say the resultant equals 158 kips. And then put a little line like this and an angle here, 37.5 degrees. That's completely defined now, right? It gives a magnitude and a direction. All right, I'm gonna stop there. I'm not coming back today. You guys go, we're done, for today. I don't wanna continue on new material. Go study. Good luck. I'll be here for office hours later, so.